loves, but we're going to start graphing a lot of the non-linear functions, the common non-linear functions. What you're going to notice really quickly is that if we know the parent functions, the rest of it kind of follows the same pattern. And so just knowing what the parent functions look like is probably the primary objective here to just graphing any function. So we're going to spend a day here working on learning how to graph just the regular parent functions. All right, so here, your number one thing, we've got, we're going to make a list of just the parent functions, the common functions, and then kind of look at some of the different ways they can be represented, both by their parent function, what it looks like in standard form, and then what the graph of each function looks like. And you're just going to have to be able to identify these today, and then in the next lesson, we're going to figure out how we would just be able to use those parent functions to graph pretty much anything. So let's start with the one that we already know. We've spent a lot of time working on it in the recent days, and that's the linear family. Okay, so the linear family, the parent function is just simply y equals x. Kind of in slope-intercept form, where the slope is 1 and the y-intercept is 0. If we want to, we know that the standard form is ax plus by equals c, but that's typically not the one that we think of. And so for practical purpose, we'll say the regular form is y equals mx plus b. Okay, where again m is the slope and b is the y-intercept. And when we graph a linear function, we always wind up with some sort of straight line. Okay, so as b changes, that kind of shifts it up and down along the y-axis, and as m changes, that changes the slope. All right, so this is the one that we really feel like we've got down. One that is closely related to the linear family is the absolute value family. And this is similar in that we're going to get straight lines. So y equals the absolute value of x. Okay, but we can't continue going down forever because if x is negative, well, that winds up giving us a positive. And so the standard form, which we're going to use in the next lesson, I'm just going to present it to you here, is y equals a times the absolute value of x minus h plus k. Okay? And so we're going to talk about what the a, the h, and the k value do in the next lesson, but suffice it to say that when you graph an absolute value function, specifically the parent form, you're going to get a v that has a slope of 1 here and negative 1 over there, and the vertex there will be at the origin. All right, the next family that you're probably most familiar with is the quadratic family, okay, or in other words, the square family. Okay, and again, there are a lot of connections between this and the absolute value family. The parent function is y equals just x squared. You may remember the standard form of this from when you were just in regular algebra class. It'd be y equals a times x minus h squared plus k. Okay, and so you can see it has a lot of the same elements as the absolute value function. It's got an a scalar out here in front. It's got the h, it's got the k, it's minus h, it's plus k. And when I go ahead and graph this, hopefully you remember that this is going to be a parabola, and its vertex is also right here at the origin. All right, well, let's go ahead and kind of do the opposite of the quadratic family, and that would be the square root family. Now, the square root family is not technically a function, and so, oh no, it is a function. I'm thinking of the other one. But anyhow, the parent form is going to be y equals the square root of x. Okay. The standard form is going to be y equals a times the square root of x minus h plus k. Okay, and again, you can see a whole lot of similarities here. We've got the a value out front. We've got the minus h. We've got the plus k. And just so you guys know, like all of these things do essentially the same thing to your parent form graph. And so that makes for a much easier graphing life here in a little bit. Anyhow, the graph, if I were to graph y equals the square root of x, if we pick some values here for x that were convenient, like 0, 0 squared is, or square root of 0 is 0, we would wind up with something like this. And it would actually be just this function reflected over the line y equals x. And you know, we don't typically graph it, but if we were to, it'd look kind of like that. And you could see that it was just kind of flipped over here around the x-axis instead of the y-axis. And that would make sense because if I solved this for x, say, square root both sides, you would get x equals y squared, and it would kind of look like that. All right, so the next family that we're going to be focusing in on is the cubic family, and that's going to be y equals x cubed. And just so that you know, the cubic family in standard form is going to be very similar to the standard form for the quadratic. We're going to say y equals a times x minus h cubed plus k. And when I graph this parent function, I'm going to get that little snaky deal. It's actually going to be very similar on one side to the cubic, but not quite. Or to the square function. But then down here, I do wind up getting negatives if I cube something, like -1 cubed would be -1. And so I wind up with negatives down there. So I get this little snake guy. The last one that we're going to be commonly looking at is the cube root. So the cubed root function is going to be like y equals, not the square root of x, but the cubed root of x. And if you kind of made the connection that the square root function was just the square function tilted, you could get a very similar process here. We'll say y equals a times the cubed root of x minus h plus k. So again, still with an a, minus h, a plus k. And this time, when I go ahead and graph it out, instead of something that goes vertical, I'm going to get something that goes horizontal. Like that. Okay, so these are the parent functions. Today you're just going to be identifying parent functions, which shouldn't be a big problem for you if you can kind of memorize the names and what they go with and what their graphs look like. That's not going to be a difficult learning target for you to master. The other thing that we've got today is piecewise functions, which is a real common thing in pre-calculus. And so here, all we're going to do is we're going to make sure, and see this is, sorry it didn't show up, but this is going to be less than or equal to 2. We just graph the function that we're given over a certain domain. And so if I have 2x plus 5, y equals, or f of x equals 2x plus 5, with a domain of x being less than or equal to 2. Well, here's 2 right here. Okay, so what I'm going to do is I'm just going to graph y equals 2x plus 5 up until 2. So I would have a y-intercept of 5. I would have a slope of 2, so up 2 to the right 1, up 2 to the right 1. I could also go down 2 to the left 1, okay, and you can see that very quickly I just have this, okay, but I just want it for less than or equal to 2. And so I'm going to have my my filled in dot here, and then I'll just connect my line, okay, and it goes forever that way. At this point, okay, I have x plus 1, but that's when x is greater than 2. And so at greater than 2, I have a y-intercept of 1. Okay, so here, I'll draw this in a different color. This isn't going to show up on my final draft. Okay, but I would have a y-intercept of 1. And I have a slope of 1, so up 1 to the right 1, up 1 to the right 1, okay? And so at this point, I would have an open dot, okay, because it's just strictly greater than 2. And then I would continue with that, and so up 1 to the right 1, up 1 to the right 1, up 1 to the right 1, and I would just go ahead and continue on with this. Oops, a little bit off there. Okay, so this is the piecewise function. For x is less than or equal to 2, okay, I have this red line. And then for x greater than 2, I have this blue line. Okay, but I definitely don't show any of this stuff over here. Okay? All right, so moving on to my second one. If x is less than or equal to 0. So sorry, this one needs to be less than or equal to 0. So 0 is my kind of cutoff here. I have 2x plus 3. So I have a y-intercept of 3, and then I have a slope of 2. So up 2 to the right 1, up 2 to the right 1. Okay, I don't need to go down 2 to the left 1 because I don't really care about anything less than 0 at this point. So there we go. All right, and then we'll do this one in a different color. We'll go ahead and say, all right, we want x squared plus 3 if x is greater than 0. Oops, I made a mistake, didn't I? I wanted this one if x is less than 0. So I actually don't want any of this stuff, sorry. I just want less than 0. So down 2 to the left 1, down 2 to the left 1, down 2 to the left 1. Okay, I want everything that's down that way. All right, so now on to my second one. I want x squared plus 3, okay, or equal to. And so when I have x squared plus 3, again, at this point, we don't really have a great way of graphing x squared plus 3 other than just doing a table, although in the next lesson we'll have an easy method to graph that, if you don't remember already. So at this point, we're just going to pick some values for x that will help us out. So if x did equal 0, I would have 0 squared plus 3, which is 3. Now, of course, I can't use 3, okay, so I'm going to be putting an open dot here, okay. Let's see, next value, try 1. 1 squared is 1, 1 plus 3 is 4, and so I'd go over 1, up 4, and I've got a spot there. Now, at this point, I really don't know exactly what it looks like, but I do remember the parent function is at least a parabola, so I'm not going to make the mistake of making it linear here. Let's try one more. How about 2? 2 squared is 4. 4 plus 3 is 7. So over 2, up 7. And so I've got a coordinate right here. And this hopefully is enough to help me graph. Remember, it's a parabola, so it's going to look something like that. And there we go. I'm done. All right, moving on to the last one. We've got kind of a problem-solving type question. So let's go ahead and read through it, looking for critical pieces of information. An express mail company charges $25 for a package weighing up to 2 pounds. Okay, and then each additional pound, or fraction of a pound, there is an additional charge of $3. So even if I just have 2.01 pounds, okay, it's just slightly over 2 pounds, well, I'm going to be charged $3. I don't get a proportional amount of that. It's the same thing. If it's 2.01 or 2.99, it's going to be the same $3 increase, okay? And so what that means is I don't get a nice smooth increasing thing. This is going to be an example of a piecewise function. It says let y equal d of x represent the cost to send a package weighing x pounds. Graph it on the interval 0 to 6. All right, well, let's think about it. If I have, we'll say d of x, this is going to be equal to 25 on what domain? Well, the domain when x is between 0, I guess not or equal to 0. If I have a package that's exactly 0 pounds, well, it doesn't exist. So greater than 0, but less than or equal to 2, okay, is just going to be equal to 25. So if I were to graph that out, okay, so along the x, I'm going to have, this is going to just be pounds. And along the y, or d of x, this is going to be total cost. Okay, so we'll stretch this out a bit. My interval just goes to 6. So 1, 2, 3, 4, 5, 6. Okay, but then for my y, or my d of x, I'm just going to do the little cheater thing here. I'm going to start at 25. And then since I'm going up by 3, I think it might be a good idea to just go by 3s. 25, 28, 31, 34, 37, 40, go up another one, 43. Okay, so here from 0 to 2, okay, again, I've got an open dot here because I can't have a package that's exactly 0 pounds. And then as I go up to 2, okay, that's just a flat $25, okay? So it doesn't matter if it's 0.01 or if it's 1.99 or even 2, okay, it's going to be exactly $25. And then, well, if I have something between, say, 3, just strictly greater than 2, but less than or equal to 3, okay, well, I have 28, okay, 25 plus 3. And so I would have an open dot here, and it would go flat to 3, and then I'd have the closed dot here. Okay, this pattern is going to continue, okay? If I have 3.01, it's going to be $31. If I have exactly 4, it's going to be there. And we can just continue with this pattern all the way until we get out as far as it told us to, which was 6. All right, and there we go. We have made a graph that represents this situation. All right, let's see. Here's your example problems for this learning target, and enjoy.